All right, let's dive into something amazing. Today, we're going on an incredible journey through one of the most intricate and fascinating pieces of biological engineering you own, your ear. So, how does it all work?
I mean, have you ever really stopped to think about that? How a simple wave of pressure moving through the air somehow becomes this rich, emotional experience inside your head? Well, that's the mystery we're going to solve. We're going to follow a single sound wave from the outside world all the way to your brain. So here's our roadmap for the trip. We'll start with the part you can see, the outer ear, which is basically a sound collector. Then we'll dive into the middle ear, this incredible mechanical amplifier. From there, it's onto the inner ear, where the real magic happens. And finally, we'll touch on the ear's secret second job, keeping you balanced. So our journey kicks off right here, in the outer ear. Its main job sounds simple, but it's absolutely crucial, to catch the sound wave and funnel it inwards. Let's use this as our map for the first part of the journey. You can see the entry point for the sound wave, the external auditory meatus. That's just the fancy scientific name for the ear canal. And you can see it leads from the outside world right up to the tympanic membrane, which you and I know as the eardrum.
You know, the shape of your outer ear isn't random at all. Every single curve, from that outer rim called the helix to the bowl in the center, the concha, is perfectly designed. Think of it like a biological satellite dish, focusing all that sound energy and channeling it straight into the ear canal.
So once it's funneled in, the sound wave travels down this canal, the external acoustic meatus. And it's not a straight shot either. It's actually got this gentle S shape, which helps provide a little protection for the super delicate eardrum at the end of the line.
And here's a really fascinating little tidbit. Have you ever coughed when you were cleaning your ears? Well, that's a real thing. It happens because a branch of the vagus nerve, which is tied into your cough reflex, also happens to run through part of your ear canal. It's just one of those surprising connections that shows how complex our body's wiring really is.
So our sound wave has reached the eardrum, which means the first stage of its journey is over. Now it's about to pass through that membrane and into the middle ear, where it's going to get a serious power-up from a tiny marvel of mechanical amplification. We are now inside the middle ear. It's this little air-filled space right behind the eardrum. The whole mission in here is to take that gentle vibration from the air and give it a massive boost, getting it ready for the next and most important stage of its journey. And the machinery that does all this boosting? It's these three tiny bones, the auditory ossicles. In order, we've got the malleus, which looks like a hammer, the incus, or anvil, and the stapes, which is shaped just like a stirrup. They form this incredible, connected, chain-like lever system. The whole system works kind of like a set of dominoes. The eardrum vibrates, and that moves the malleus. The malleus then moves the incus, which then pushes the stapes. This whole mechanical chain reaction concentrates the force of the vibration, ending with the tiny stapes pushing into the inner ear, just like a piston. The ear also has this amazing built-in safety feature. When you're hit with a really loud noise, two tiny muscles, the tensor tympani and the stapedius, they contract automatically. They stiffen up that whole chain of bones, dampening the vibrations, to protect the delicate structures of the inner ear from getting damaged. It's basically an automatic volume limiter. And finally, this little chamber has to manage air pressure. That's what the eustachian tube is for. It connects the middle ear to the back of your throat. You know when you're on an airplane and your ears feel blocked? That's a pressure difference. That pop you feel when you swallow or yawn? Yep, that's this tube opening up to equalize everything. Okay, so we've collected the sound, we've amplified it, and now we arrive at the final and most complex stage. We're going into the inner ear, where that mechanical energy gets transformed or transduced into the electrical language of the brain. This right here is the inner ear, also known as the labyrinth. It's a hollowed-out section of your temporal bone. And you can see two main parts. There's that snail-shaped thing, the cochlea. That's our destination for hearing. And then there are the semicircular canals, which we'll visit in a minute because they handle your balance. Now, this is really crucial. The whole labyrinth is filled with two different types of fluid. You've got the perilymph, which fills the main bony cavity, and then floating inside that, you have these delicate ducts that are filled with endolymph. This whole fluid within a fluid design is the key to everything that's about to happen. This slide is great because it really helps visualize the core concept. Let's just imagine we take that snail-shaped cochlea and unroll it into a straight tube. Remember the stapes, that little piston? Well, it's pushing on the oval window at one end, and that creates a pressure wave in the perilymph fluid. This wave travels all the way down the top chamber, the scala vestibuli.
And here it is. This is the absolute heart of the matter. As that fluid wave travels along, it makes a flexible membrane in the middle of the tube, the basilar membrane, start to vibrate. And sitting on top of this membrane is the incredible organ of Corti. The vibration makes its thousands of tiny hair cells bend. And that physical bending, that is the trigger. It opens up ion channels, creates a tiny electrical spark, a nerve signal that gets sent to the brain. This is the moment. This is how a physical vibration becomes a neurological event. So just how sensitive is this system? In this tiny, fluid-filled space, there are up to 30,000 of these delicate hair cells. And here's the critical part. Unlike a lot of cells in your body, these hair cells do not regenerate. Damage to them from things like loud noise or just age is permanent, and it's the main cause of most hearing loss. It makes protecting them so important. That number is just staggering. So before we finish our journey of sound, let's just quickly explore the other amazing function of the inner ear's labyrinth, your sense of balance.
The amazing part is that it uses the same basic principle of fluid and hair cells. The 3 semicircular canals are arranged in 3 different planes. So when you rotate your head, the endolymph fluid inside them sloshes around, it bends hair cells, and that tells your brain about the rotation. Meanwhile, the utricle and saccule, they handle linear motion, like speeding up in a car, and also your head's position relative to gravity.
So let's just put it all together one last time. Our journey started on the left with a simple funnel designed to catch a physical wave of pressure. It ends over on the right with this complex labyrinth that transforms that pressure wave into the rich electrical language of the brain. An absolutely incredible, seamless process that's happening right now inside your head.
And all of this brings us to a final, kind of mind-bending thought. The ear is a translator. It translates physical vibration, but the perception, the music, the emotion, that all happens in the brain. So if a tree falls in the forest and no one's there to hear it, sure, the vibrations are real, but is the sound? It really makes you think, doesn't it? Where does the physical world end and our experience of it truly begin?